Okay, so let's start. I think that maybe we can kind of fast recap everything from the previous half of the chapter. So in the previous half, we talked about like the history a bit, about the origins of modern particle physics here. We talked about the zigzag picture of the electron. We talked that the Dirac spinor can be divided into like in a pair of two spinors, alpha and beta here, with two different van der Waals indices. And therefore we can reinterpret the electron, for example, as moving in a kind of like zigzag shape, like depicted here. Yeah. And what we had more, we also talked about electroweak interactions, the basically asymmetry of those, because in the case of the weak interactions, sorry, I can't put the book into the camera view table. So okay, what we have here is the depiction basically of the antisymmetry of the weak interactions, because kind of every particle we know, like I think maybe leptons or fermions, don't remember the exact thing. So anyway, like any particle could be described in that zigzag approach, and the weak force bosons W or Z here, they will only act with the zig part of our particle description and not with the zag part. Yeah, and that kind of leads to the asymmetry in the weak forces. We can take a look at the Feynman graphs here, as Alex asked before. So here you can see Feynman graphs on the left without zigzags, on the right with zigzags. And what we have here, as you can see, like the white arrow, it represents the electric charge, and it kind of is in the other direction of the particle, like movement line. So it means that it has negative charge. So basically we have electron here, and electron is flying in some trajectory. It interacts with a photon here, and afterwards, like with the, as I think like considering all the conservation laws, basically like momentum conservation here, the electron will fly somewhere to the left now after the interaction with the photon here. And I think in this case we have like absorption of the photon, in this case we have emission of the photon, and in this case it's called something like interaction with the photon, something, yeah. So Alex, does it make them like a bit similar to you, or easier to understand? Maybe you have some direct questions. Alex? Alex, do you hear me or no? And any one of you guys, like, do you hear me well?
Fine, I can hear you, Slava.
Okay. Yeah, I just was confused because Alex was not responding for some reason.
No, it was a very weird problem on here. My end, I guess. I could hear sounds, but it wasn't muted, but I could hear no voices.
Mm-hmm.
But it seems to work off the rest of the phone.
Okay, so now you hear me well, right?
Yes, perfectly fine now.
Okay, so here we have like maybe one of the most complex Feynman graphs, I think, from the book, right? So we have like a beta decay of neutron, where he decays in the proton, electron, and antineutrino here. So those black arrows are just like the particle directions, and white arrows are for the charges. So electron has backward white arrow, and proton has forward white atom arrow, and antineutrino has no white arrows in there. And also you can see that movement thing, it kind of shows that antineutrino moves backwards in space-time, basically.
So do the black arrows say anything about direction, or only that they're moving forward in time?
I think it's also probably it's also about moving in space and time together, because from the later subchapters we found out that actually it's PT symmetry, so like space-time reflection, which kind of separates antiparticles from the particles. So I think it's kind of moving backwards in a space-time. So it will move actually backwards in space. So that's true. It corresponds to the movement of the particle in space. But it seems it also will move kind of backwards in time also.
Yeah, I've been thinking about that a little bit. So how can we really distinguish something moving backwards in time from something moving in the opposite direction? Wouldn't that be the same thing?
I think from relativity perspective, it's the same thing, because like you have like space and time merging into one thing. Yeah, but actually in the book we don't have a lot of like Feynman diagrams theory, so you shouldn't be, I think, too much how to say, like sure that you're understanding those right from the Road to Reality book. So probably Roger Penrose thinks that we should consult like additional literature here, some other books, to understand those maybe better. Yeah,
as long as I understand the figures he's showing, I'm happy. But yeah, that would probably help.
mm-hmm. Yeah, so, and on that picture we had like move to the like 2-point connection here instead of 1-point interaction. So every like beta decay should be connected with some kind of weak boson, like W boson in that case. And also we talked about Wu experiment, where she and her team find out about the mirror reflecting not anti-symmetry, asymmetry. Yeah, parity. So like not how to say that, like asymmetry of the physics, due to the parity transformation, basically. We talked about neutrinos also a bit, and we talked about the Cpt stuff, like Cpt theorem, different. Have some delay in the book movements here. Yeah, so we talked about like charge conjugation, parity transformation, and time transformation. So, and that just the existence of Cpt theorem, which tells us that if you apply all three transformations at once, then every like physical interaction will be preserved and physics will remain invariant. Yeah, he also talked here about K0 meson a bit, and he said that the decay of the K0 meson will violate something, will be non-invariant under Cp transformation. Okay, I was wondering about that K0 meson because we will talk about that today also. Yeah, so basically at the end of that subchapter, we came up with the rule to find the antiparticles. So we can...
And those correspond to the charge conjugation, right?
Charge, I think that no, because on the previous page it was written that it should correspond to the yeah, but to charge also. Yeah, sorry, because like it seems that we can consider Cpt symmetry as a whole as some kind of identity. So therefore, you can take charge, either charge symmetry or space-time symmetry. So it will be the same. So either you will switch like space-time direction for the particle for it to become the antiparticle, or you will kind of switch charges.
So if you have the opposite, I'm not sure that's correct, the what do you call it, space-time symmetry, then that is making it an antiparticle. It's just the same as the charge thing, inverted space-time object. Is that correct?
Oh, okay, let's take a look at the direct paragraph here. So here it says like that parity plus time symmetry, it is the same as like getting the antiparticle. And it says that Cpt theorem provides us with perspective on antiparticles. Yeah, that's true. And we can regard C, the interchange of particles with their antiparticles, as equivalent to the Pt. So it seems that it's the same.
Yeah, but to be clear, he's saying that the reflection of the Pt would be the antiparticle. But if you wouldn't have a reflection, I would assume it's just the normal particle.
But you will always have the reflection, always. Maybe it will be identical as in the case of the photon, right? But you will you can have a particle which is antiparticle to itself, but you will also have the reflection. Anyway.
Yeah, of course, yeah, you would have both. Yeah.
Okay, so and the rule to find the antiparticle here was, so we kind of needed to describe how the particles will interact weakly, and Penrose just kind of explicitly defines it here. He says that if you will take the leptons, so it's just like electrons, and their heavier sister particles, muons, tauons, and corresponding neutrinos, and also quarks that will compose the protons and neutrons and other hadrons actually. So if we say about those as particles, and basically those leptons are particles and they will have Hicks which will undergo the weak interactions. So, and they are antiparticles using the Pt reflection will undergo the weak force using their Zach's part actually. Okay, yeah, so that's kind of it. Talking about the previous subchapters, let's try and take a look at the new one. So I think I will try to move fast because I only have 50 minutes today. 50 minutes is too small amount of time. Anyway, yeah.
It's fine for me if we don't finish all of it, but yeah, we'll decide.
Yeah, we'll see. Anyway, so in this subchapter we are talking about that there is actually an underlying pattern to all of the things we described before, and like in the previous subchapters we had kind of botanical notes, so we just talked about a lot of kind of interactions, particles, etc., but we haven't talked about the some kind of like unifying theory or something for those. Yeah, and what we have here, he says that in the Electroweak theorem there is actually special symmetry relating the weak bosons and photon, and it is described by the group SU2 multiplied by U1. And he says, or more correctly, U2, because there is some kind of, I think, isomorphism. I think it's isomorphic. So, like, if you multiply circle by a four-dimensional sphere, you will have U2 group. But I saw on the physics stack exchange that it's not correct to think about U2 as the symmetry. And they have some kind of special SU2 and U1 groups in there, actually. So it's interesting why Penrose said here more correctly U2. So it's a nice question.
Yeah, you should check out the footnote. I think it was worth reading.
Ah, you want to see a footnote? Okay.
I've seen it, but maybe it's interesting for others. I thought it was a good footnote.
Okay, so he says that this group can be expressed as SU2 by U1 factored by Z2. However, there is more than one such subgroup, so this notation is not fully explicit. The notation U2 automatically picks out the correct one. It seems that the reason that the Electroweak symmetry group is not conventionally referred to as U2 is that this does not easily extend to the symmetry of the full standard model, which also incorporates the strong symmetry group SU3, the full group being Okay, so there are some kinds of more details in there, but like overall we can think about this group as SU2 multiplied by U1 or just U2. Okay, and he says that this symmetry also interrelates the Zig parts of various leptons and quarks, and the idea has the consequence that from a more primitive perspective, all of the bosons and also weak bosons and photon can in certain sense be continuously rotated into one another, and actually we will see that on the next page. Okay, and he says that symmetry is pretty subtle. So yeah, and it's subtle because pure electromagnetism is reflection invariant, whereas weak interactions, as we know, are non-invariant under the reflection. Okay, and photon appears to be clearly single out because it is a massless particle, and our weak bosons, they're kind of massive ones. And afterwards he gives us pretty hard paragraph about the three-pronged Feynman graphs. So in the figure 25.12 you will see that on the next page he has different interactions between the weak bosons or with photon, and he says there are just two of them, but the fact that there are any at all is an expression of a non-linearity in the free gauge field, which arises from the gauge group being non-abelian, blah blah blah. So basically it just talks about the non-abelian gauge theory. So our new group U2 will be non-abelian, and therefore he says that we will have some non-linearities, and in terms of Feynman diagrams, it just arises as existence of those three-pronged diagrams, which you can see here at the figure 25.12. Okay, so, and what we have here is just three-particle interaction, and you can have like one, let me see, so the Z0 lines are double without arrow, and W plus or minus lines are double with white arrows, and photon is that wiggly line here. So you can see that you can have only like those three Feynman diagrams in existence, basically. Yeah, and somehow it encodes non-linearity in the basically in the physics equations which will arise from that gauge theory. Seems that I need to zoom out a bit because it's too close. Okay, and he just talks about electromagnetism here, and that we have abelian gauge group, so commutative basically, U1, and consequently there is no analogous three-pronged Feynman diagrams involving only photons, and this would have given rise to non-linearities in the source-free Maxwell field equations. Yeah, and he says that analogous statement applies to the n-pronged vertices with n greater than 2, and just addresses us to take a look at the fiber bundle gauge connections and theories. So yeah, it seems like not too specialist for me, because it's not really useful for us as a newbies.
Any idea what source free refers to?
What source?
It says source free Maxwell field. I don't know what that refers to, being source free.
Yeah, like no charges, I think. So if you remove everything from the Maxwell equations, you'll have like the divergence parts, the waves. So you will have only photons, like only electromagnetism gauge bosons basically in there, I think. So like only like field propagators or something instead. So that's kind of the same equation which is used to describe the photon as a wave. Maybe you can recall that, or I should address you to the older videos we had on the previous call about electromagnetism. So there, I guess Joe actually made some presentation about those, like small derivation of the wave nature of the photon. Okay, so, and the next paragraph is pretty interesting because he says that like how we can reconcile these seemingly blatant deviations from symmetry with the required goal of a unified symmetrical theory. Basically, he just wants to say that like how can we find out how that U2 symmetry actually relates to the particles, and his idea is pretty simple. So he just wants to take a look at the Hermitian matrices 2 by 2. That's exactly the elements of the U2 group, right? So, and he says we may imagine that the two real diagonal elements are corresponding to the Z0 and gamma of photon, because they, after if you try to conjugate them, you will still get the real numbers yet, and it kind of corresponds to the particle-antiparticle relation for those, because they're the same as their respective antiparticles. And in similar kind of things for the bosons W plus and W minus. We can kind of relate those with the complex conjugates, of diagonal like complex numbers, and they will be kind of complex conjugates of each other. Yeah, and therefore after the like antiparticle operator applied, basically, which is kind of complex conjugation. Sorry, not complex Hermitian conjugation actually. So I think that he just says that you can see that Hermitian matrices, 2x2 matrices, they are kind of correspond to the particle-antiparticle relation here for the weak force. Yeah, and he says that a general U2 transformation of this Hermitian matrix, and he says you can pre-multiplicate or post-multiplicate it by another Hermitian matrix, thus churn around the elements of this Hermitian matrix in very specific ways, but its Hermitian character is always preserved. So basically you will still have some kind of the similar relations. So you'll have like two bosons which are antiparticles for themselves yet, and two of diagonal ones which are just like antiparticles of each other or something. So he just basically connects 2x2 Hermitian matrices to the particle-antiparticle relations here. Yeah. And he adds that in fact this analogy is very close to the way in which U1 indeed acts in Electroweak theorem. And he says that there will be some complications because of the Weinberg angle here. We'll talk about this later. Okay, and he also talks more about the asymmetry that we see in the actual world for the like weak force. Yeah, and that comes about in Electroweak theory merely because nature chooses certain particular combinations. So particular quantum superpositions of these elements to be realized as actual free particles. So basically I think the question here is like why, if we have U2 symmetry, we have that like mirror asymmetry in the weak force. So like why symmetry breaks basically. And he says that the reason for that is that kind of we can think that maybe nature takes some kind of a subset only for those like fixed matrices or something. So some particular bosons will be observed in nature only. Yeah, and he says that that asymmetry is about the thing we saw with like Zik and Zak lines in the Feynman diagrams and the weak interaction bosons. And actually, theoretically, we could have like other variants for those. For example, for a photon, we could have some Y capital particle, which will see only the Zak part of the particle. And he says that we could retrieve our original, so it will be some kind of combination of Z0 and gamma here. So we kind of will churn around, add those, make some kind of superposition using some complex matrix, for example. And yeah, he says that even so, like there would be many other possible such superpositions which could equally have played the role of the photon had nature chosen things in some other way. So basically the question is, why do we have a photon like that and those weak symmetry bosons? And actually the whole next big paragraph, almost the whole page here, is discussing that theme. And he says that like a key issue is what criteria does nature adopt in allowing us to find certain particular superpositions as free particles and not others. And the basic answer is that for a free particle we need it to be an eigenstate of a mass. So we need to know what it is that determines the mass of particles generally. Yeah, and here we cannot expect full symmetry under U2. In other words, mass involves some kind of symmetry breaking. And the idea here is that like the asymmetry that we actually observe today in particle interactions is the result of a spontaneous symmetry breaking that is taken to have occurred in the early stages of the universe. And before that, actually all of those particles like were in extremely conditions, like with extremely high temperatures, and actually U2 symmetry at that time held exactly. So those four bosons like W plus, W minus, D0 and gamma, they all would be like completely equivalent to many other sets of the quantum superpositions of these particles. And yeah, and Photon was on the equal footing with all sorts of other combinations that could arise in this way. But as this idea goes, actually the universe cooled, and by that it means that temperature fall below 10 to the power of 16 kelvins, and it happened at the time of about 10 to minus 12 seconds after the Big Bang, and the particular four bosons that we observe today were frozen out by this process of the spontaneous symmetry breaking and cooling, basically. So, and that's why we see the asymmetry observed today. But theoretically, it was present in the early times of the existence of the universe. Yeah, and actually Penrose is not happy with that also, so it seems kind of strange. Like, why can we use the SU2 symmetry here if it's broken? So we will talk about that at the end of the subchapter, and he will give us some clues to it and maybe new pathways to tackle it somehow. Yeah. So anyway, at the time when symmetry held, all of those bosons were effectively massless, so they had no mass. And actually one more thing was frozen, which is called the Higgs field. And actually the Higgs field and like interaction with it of our particles is the exact thing which gives the particles their masses. So yeah, and also to the quarks, etc. So, and how does it do this? And Penrose says that actually the full details of this interaction unfortunately remain outside the scope of this book. So maybe we will see some ingredients later, but you should take a look elsewhere if you want to know the details. Anyway, we can think about the Higgs field as something conceived by the coefficients in our zigzag representation of the Dirac equation. So you can recall those square roots basically of 2 multiplied over m in the Dirac equation, which we called like coupling constants. And basically those constants are essentially the Higgs field. And I think that it will enter there as an interaction. So therefore you can see the next picture here, 25.13, which just tells that in our zigzag picture of the universe, we can think about the Higgs field interacting with the particle at the time when it changes its direction, basically. So it changes zig to zag and zag to zig. So those like moments are exactly the moments when the particle will have the mass, and therefore like the Higgs field will kind of interact with it, while particle isn't kind of moving with speed of light in there, I think. Yeah. So in the next paragraph, he says about the frozen Higgs field. So it kind of has the constant value everywhere, which is frozen, and this value kind of fixes the overall scale for the determination of the masses of all particles, and different values of those masses being scaled by some numerical factor that depends upon the details of each particular particle. So probably there will be some kind of differences between the coupling constants for different particles. So interaction with the Higgs field will be different for each particle for some inner reasons. Yeah, and actually he says that he will postpone the assessment of this extraordinary collection of ideas until chapter 28, where it fits more appropriately. So we'll talk about the, I think, Big Bang there and inflationary theories or maybe other theories of the early universe. So anyway, the last paragraph here just says that Electroweak theory actually was really successful. It predicted the zero boson, and also it predicted the masses of the bosons for the weak interactions pretty, how to say that, pretty accurate. So theory was first, experiments in CERN were afterwards, and they confirmed with a good precision that the modern observed values are consistent with the Electroweak theory, and numerous other kinds of predictions have also been confirmed. So the Electroweak theory stands in excellent shape observationally at the time of the writing of that book. So I think like 10 or 15 years ago. That's it for the first subchapter for today. Any questions?
I think I have this very basic question. How I don't get why does the symmetry enters the explanation here? What exactly does it mean that certain particle possess a certain symmetry?
Yeah, it seems to me that it's kind of hard currently to understand that, because actually we shouldn't be talking about particles. I think we should be talking about fields. And from the fields perspective, probably that will be more evident. So yeah, so we basically have kind of like space-time, right? And over it we will have a bundle with those symmetries, symmetry groups basically at each point. And I think you kind of can adjust every point of space-time using the elements of those groups. But it's not particularly like about the particles, I think.
The group is acting on some particular structure that
so particles arise as some kind of representations of those symmetry groups. So you will have some entities like spinors or vectors or something like that, and those group elements will act on those particles, I think. Yeah, and like every symmetry is actually connected with force, and therefore it's also connected with different type of a charge. So we will have some kind of a charge as we have it in the like electromagnetic field, right? And there should be a charge for the weak field also. But Penrose do not talk about it yet for some reason. I do not know why. So there should be something which is called, I think, like weak isospin or something. I'm not aware about like details of it. So maybe in the next chapter he will talk more about those. Yeah, so all we know from that subchapter is that this kind of electroweak theory could be united into U2 symmetry, because there is some connection between those Hermitian matrices and the particles being interpreted together also as matrix, I think. So he kind of condensed all the 4 bosons here into one matrix, like this, like Z0, gamma, W plus, W minus, and those Hermitian matrices, they will be self-contained in the U2, and they could be acted with other U2 matrices on it, and the hermicity property will be preserved there.
So these 4 particles are, this U2 is the action to be exerted on the space-time, or?
Yeah, so it seems to me, as he says here, that if you multiply that representation of the bosons as matrix by any other Hermitian matrix, then you will have some kind of new particles which will play the same role actually as the previous bosons played. But now they will be kind of superpositions of those particles. But you'll have the same properties. So basically, that symmetry lies not in the real universe, but in the universe before it, at the initial universe, before the Big Bang. So it seems to me that that symmetry was in there before the spontaneous symmetry breaking, and you kind of could have a chance there to kind of switch the bosons to some other particles instead or something. So you kind of could have more variance there for the candidates to act for the electroweak interactions.
I will accept that. It's a bit still confusing. I will do some reading afterwards.
Yeah, I'm not sure about what I'm talking here also. So don't be confused that I understand everything. I do not. So I only have some intuition behind his words here, and that's it. So we definitely need a lot, to do a lot more reading to understand that better. Yeah, that's totally true.
You're in good company there.
So yeah, I think that we should continue, and anyway, we will have, I think, additional call to talk more about those symmetries and what do they mean for every kind of force. So I think we should discuss basically the gauge theories in a more detailed way. So I think we will have a special call dedicated to those later. So, and here we come to a lot of new, how to say that, particle names, right? So, anyway, we haven't talked yet about strong interactions and quantum chromodynamics or theory of strong interactions in the other half of the standard model. And he says that it may seem an odd name, since the chroma means color, and color has nothing to do with the ordinary concept of the color here. But anyway, we should go back a little and talk about hadrons, or hadrons just, right? Sorry, one moment. Hadrons.
A large hadron collider, I think.
Yeah. So, and neutrons and protons are particular examples of hadrons. And what is hadron? Hadron. Okay, so the name. What is the correct pronunciation?
Hadron.
Using hadron.
Yeah, I'm pretty sure it's hadron.
So without silent H, yeah, because like usually it's. I thought it should be silent for some reason. Don't know why. So like here in Ukraine we call those, I think, hadrons, like just hadrons. But I can say
we'll understand you either way.
Yeah. Okay. Anyway, so the name hadron is from the Greek hadros, meaning bulky. So they're kind of massive particles. Why? Because they he says here that they are more massive of the basic particles of nature and they take part in strong interactions. Okay, so all of the hadrons take part in the strong interactions. Okay. And he says that hadrons actually divided into two families, which correspond to fermions and bosons. And basically, fermion hadrons are called baryons, and boson hadrons are called mesons. Okay, and from the previous theory, we can recall that fermions are basically like matter particles, and bosons are kind of propagators for the interactions. And fermions are antisymmetric, have 1/2 spin, and bosons have integer spin and are symmetric actually. Okay, so, and basically hadrons could be among fermions and among bosons too. So, and we have two more names for those, baryons and mesons. Great. So, and all hadrons are taken to be composed of quarks. In conventional theory, okay, and baryons are the ordinary nucleons, particles. So baryons are ordinary nucleons, like neutrons, protons, and their heavier cousins called hyperons, discovered in cosmic ray showers and in particle accelerators. And okay, and mesons were a remarkable theoretical prediction by the Hideki Yukawa in 1934 on the basis of his analysis of nuclear forces, these being the pions or like p mesons that were eventually found by the Powell in 1947 in cosmic ray tracks. Now many other meson cousins to the pion are also known. Yeah, and more to it, like the term baryon comes from the Greek baris, meaning heavy, so one more time heavy. Okay, and in contrast with the lepton, which comes from leptos, meaning small. I think Penrose should avoid those etymology questions here because it kind of confuses the overall picture. Anyway, the leptons are the electron, as we could recall, and its sister particles, muon and the tauon, and also corresponding neutrinos and antiparticles together, which are called like antileptons here. Okay, and both leptons and baryons, they are all fermions. But leptons are distinguished from baryons by the fact that they do not directly indulge into the strong interactions. So basically, among the field, no, not the field, but a group of fermions, we have two subgroups, right? So leptons and baryons, and leptons do not interact strongly, but baryons do. Okay, and he says that, which is perhaps the main reason that leptons tend to be much less massive than baryons, because a lot of energy and therefore mass is concentrated in the strong force interactions between the quarks in the like protons, for example. Yeah, and he says, but tau 1 is an exception, being almost twice as massive as the proton or the neutron. Interesting, interesting why. Okay, and he says that since the late 1940s, vast numbers of hadrons have been discovered in cosmic rays and in accelerators. So you can see a lot of those Greek letters here, like lambda, sigma, I don't know, that later maybe theta capital, I think, or something. And also deltas, omegas, rhos, some omegas again, but small case. So a lot of...
Maybe the first one is new.
What?
I think the first one might be new. Instead of new, it's new.
First one or...
The upside down V.
It's lambda.
Yeah, it's lambda. It's not new. It's lambda, yeah.
Okay, it's that.
So new you have here. I don't know how new capital is written actually. never saw that.
That one's eta.
That one?
Just before the K.
Yeah, that's the one I was thinking about. It's a little confusing.
Yeah.
So the one that the figure's about currently is C. And the third from the last one is eta.
Ah, it's eta. Okay. Yeah, Greek letters. Okay, so let's go further. He says that actually many of these particles have higher spin. Sisters and brothers, I think, referred to as Regge recurrences. So, and probably we will see those in chapter 31 somewhere. This would have been totally bewildering, he says, that had it not been for the fact that they were observed to fall into certain families. So basically we have that big hadron zoo, and kind of experiments showed us that they fall into certain families called multiplets, and the kind of understanding of those multiplets was obtained by the Gell-Mann and Niemann in 1961 on the basis that these multiplets provide representations of the group SU3, or more correctly SU3 factored by Z3 here. Yeah, basically it's kind of like group, like Z3 is just a cycle group of 3 elements, which we have seen in the roots of unity for the complex numbers, and basically it will just divide SU3 basically by 3. So we will have, instead of one SU3 element, groups of 3 SU3 elements in there. Okay, yeah, and he even addresses us here to the chapter 5. You can also take a look in there. Penrose discusses quantum numbers there, so basically associated quantities with the particles, which are preserved. So some of those are additively preserved. Basically, you should kind of add those for the composite constructions, like molecules or a set of particles. And some of them are multiplicative ones, so you should multiply those. Anyway, when we move further, he says like the best way of understanding those SU3 symmetries was to kind of introduce the quarks and to suppose that each hadron is constructed out of certain basic entities of spin 1/2 that Gell-Mann Christian quarks. So, and they had 3 types of those, and antiquarks also 3 types, and each baryon. So, and baryon is like fermion, which strongly interacts basically, is taken to consist of just 3 of these quarks, and each meson of 1 quark and the 1 antiquark. Okay, so mesons consist from like 2 quarks and baryons from 3 quarks. Yeah, and they had three flavors, so-called flavors of the quarks there, which were called up, down, and strange. And mysterious feature of those quarks were that they had, or have actually, have to possess fractional electric charge. So in proton charge units, they should be like 2/3, -1/3, and also -1/3 respectively. So therefore, because of those implausible seeming values for the charges, people thought about those as unreal at first, and they kind of just provided some nice bookkeeping thing here to make like a nice picture, theoretical picture for the different representations of SU3 factored by Z3 group. And the bookkeeping only worked, however, if the quarks were treated as entities that satisfied the Ron statistics for particles of spin 1/2. And it means that instead of being anti-symmetries, they should have been symmetrical ones. So it also added more questions to the theory. And afterwards, Penrose just kind of gives us two examples, which should kind of show us why quarks should be symmetrical instead of being anti-symmetrical. So let's take a look at the first example here, and the first example is he calls it decouplet of 10, basically set of 10 particles with spin 3/2, and actually that and I think decouplet is maybe from Decay, like 10. So basically we have set of 10 particles here, and it predicted the existence of that omega minus particle, and was, I think, invented by Gelman and Niemann in 1962. Yeah, and all other particles at the time were already known from that set, and the prediction was confirmed in 2 years. So if you decompose those into the quarks, you will see that structure. So you have like 3 U's, 2 U's and D, U, D, D, 3 D's, and the same thing here, but now you will introduce strange quark here also, so you have like UU and S, and UDS and DDS. So basically you just kind of add one more strange quark here, and afterwards you just replace U's with D's. So it just works like that. And the same way in this third line, you just replace 2 U's with S, and now you can have only 2 available particles. And the last one, omega, is just a combination of 3 strange quarks. Okay, and why that kind of scheme works? So why do those particles exist? Why they are observable? Penrose says that it's because they have symmetrical nature, basically. So if our quarks had anti-symmetrical nature, then we basically would have those like UUU and UUD particles, for example, vanishing. So the quantum amplitudes for those will vanish, and we will have like 0 probability of observing those particles. But we see those, we observe those, and therefore they are not vanishing. That's one thing here. And another thing is that they are symmetrical actually, because if we kind of change 2 quarks with places of 2 quarks, like having UUD as initial value and afterwards having UDU, we cannot distinguish between those. So they will be yet the same particle, which is UUD here, and is actually a delta plus particle.
Because they're in the same order. If you
yeah, so basically it doesn't matter. So order doesn't matter for those. Yeah. And because of that, it seems that basically from the experience, from the experiments, they implied that quarks should be actually symmetrical instead of being antisymmetrical. But still, that should have 1/2 spin, because those particles all had like spin 3/2, and spin 3/2 means that all the 3 quark spins, each being of value 1/2, are aligned so symmetrically, and so there is a complete symmetry with regard to the spin aspect of this state. And if the quarks behaved as fermions, then we would get antisymmetry under interchange of the quarks, not symmetry, which is inconsistent with this picture. So that's kind of the first example. And the second example, I think we should just skip that because I do not understand that nicely. So basically it just has 8 spin 1/2 particles, and we will have some similar contradiction in there. So I think you should, if you're interested in that particular example, please take a look at the additional literature, because it's just not enough information in the book to talk about that example nicely. So that's it for 25.6. Any questions, additions?
I don't know if anyone would have any sample to recall and remember all those fundamental particles. It should be easy because there are only 16 of those, but then you are making combination from few of those, and those combinations you will pack to the sets and so on and so forth. It's so complicated when you read this kind of text. So one should have a clear picture what is what.
Yeah. Actually,
to understand anything.
Actually, while I've been reading that chapter, I've been almost all the time thinking about some kind of a table, like we see in the Wikipedia for the standard model. So I kind of strived for making one or something, or seeing some kind of a graph where we could see how different particles are generated from different kinds of more basic ones.
Exactly. And you can have kind of at times you have a clear picture what is what, but then when week and a month goes, then you are totally lost when you take a look and try to remember what is what. Actually, this week I forgot to mention that I found this pentaquark. I don't know if you have heard. A pentaquark that has 4 quarks and then the antiquark that makes it a kind of a baryon at the end. But
it's kind of
Joe knows these kind of things.
It sounds misleading to have a word quark in his name, actually.
I have no idea why it's pentaquark.
Oh, you're thinking quad, or?
Chris, I saw that Chris in beta chat, he asked about like that his understanding is that there are 6 quarks, up, down, strange, charm, bottom, or charm, top and bottom, and actually that's true, and that's the material for the next subchapter. So actually, historically, SU3 symmetry at first was considered with those 3 quarks only, like up, down, and strange. But because of the strange discrepancies in the fermionic bosonic nature of the quarks, they needed to introduce what is called color. And that color scene actually, I think, led to the forming or adding 3 more quarks. And on the next page, actually, you will see for every color the corresponding quark here. So you'll have like 9 quarks from the previous ones, and you also see the added quarks which are actually charm top and bottom quarks. And at the end of that subchapter, Penrose will set that like the main role of the group SU3 in the standard model has moved from the flavor symmetry. So the first three are concerned only with the flavor symmetry. And that flavor SU3 symmetry moved to the color symmetry actually of the present day standard model. So basically SU3 symmetry now is at the other place or something. So the meaning of it shifted. Yeah, and therefore we will talk about 3 generations of matter actually afterwards. Yeah. But I think we will do that next time because I need to go already soon. So.
Okay. Thanks. Thanks for the lesson.
Yeah. So let's plan the next meeting.